Welcome to Earth and Sky Camp. The hands-on learning activities that I'm going to show you can increase anyone's understanding of the world. The app's 18th map is of the sky. It uses the same 24 squares, and each square has the same blue and red zone. Looking up from the Earth, everything in the sky appears to be moving. Clouds randomly drift around, but the movement of the sun and the stars repeats the same cycle every year. The moon and the planets move according to their own cycles. Every day the sun rises in the east, and when the sun sets in the west, you initially see whatever stars are to the east of it. These stars will also set in the west before the sun rises again in the east. On the sky map, the east and west directions are reversed. East is on the left side. The shaded areas indicate the Milky Way. All of the stars you can see without a telescope are in the Milky Way galaxy. It's a spiral galaxy that is shaped like a flat disk. There are no images of it, but there are images of hundreds of thousands of similarly shaped galaxies that can be seen with powerful telescopes. Our sun is in the thin middle layer of the galactic disk. Stars in the sky map's shaded areas are also in this thin disk, which is colored green in the diagram. Other stars are in the beige-colored thick disk. These stars surround our galaxy's center and its thin disk. There is also a galactic halo above and below the disks that contains clusters of a relatively small number of stars. Our sun is between the Perseus and Sagittarius arms of our galaxy. The Sagittarius arm is between us and the center of the galaxy. This is where the Perseus and Sagittarius constellations appear on the sky map. A cross mark indicates the galactic center to the right of Sagittarius. 180 degrees away is a cross mark to the lower left of Perseus. This is the point on the Perseus arm that is in the opposite direction of the center. There is also a cross mark for the North Galactic Pole near the center of the map, and one that indicates the South Galactic Pole 180 degrees away on the right side. One of the concepts that a star globe helps you visualize is the relationship of the Milky Way to the galactic poles. The North Galactic Pole is positioned at the top of the ball on the left, and the South Galactic Pole is at the top of the ball on the right. The Milky Way can be seen to run halfway between the poles. The grid on the sky map corresponds to the grid of latitude and longitude on the Earth, but it is projected out into space. The celestial equator is the Earth's equator projected out into space. The curved line is the ecliptic. It's the apparent path that the sun travels in the course of 1 year. The moon and the planets also move along the ecliptic. Instead of latitude and longitude, positions in the sky are given in units of declination and right ascension. Declination corresponds to latitude, and it is measured with the same north and south degrees. However, degrees of west and east longitude are measured with 24 hours of right ascension. Right ascension hours are numbered from 0 to 23, moving from right to left on the map. Hours are each divided into 60 minutes, and minutes are divided into 60 seconds. On the spring equinox, the sun crosses the celestial equator. The sun is indicated by a yellow disk on the map. The 5 visible planets are also displayed at their positions on the ecliptic. These positions are for the spring of 2023. Saturn and Jupiter are represented by blue and green disks. Mars is red, and Venus and Mercury are orange and brown. Every day, the sun moves about 2 minutes of right ascension to the left, which is about 1 hour per month. The moon moves about 49 minutes of right ascension every day. It travels the full length of the ecliptic every month. After 3 months, the sun will reach its highest position in the sky for people living in the northern hemisphere. This is the summer solstice. In places like Australia, it is winter time and the sun is in its lowest position. Notice that the app lets you replace the hours of right ascension with the months of the year. June is winter time down under. You can now see a crescent moon to the left of Mars. On the autumn equinox, the sun again crosses the celestial equator. Mercury and Venus have traveled along with the sun. All the planets usually move to the left, but the positions of Saturn and Jupiter have not changed very much. In fact, Saturn has actually moved slightly to the right. This is because all of the planets will at some time start moving in the opposite direction. This is called retrograde, and it's due to the relationship between the orbits of the Earth and the other planets around the sun. The sun reaches its furthest point south on the ecliptic on the winter solstice. In 2023, the moon is close to Jupiter and will be full in 7 days. Note, Mercury appears inside the sun's disk. It will actually be hidden behind it. All of the planets are shown larger than they actually appear. On rare occasions, Mercury and Venus do pass in front of the sun, but they are so tiny in size, in comparison, that you wouldn't notice it. Solstices and equinoxes occur because the axis around which the Earth rotates every 24 hours is not perpendicular to the plane of its orbit around the sun every 365 days. The sun moves 23.5 degrees above and below the celestial equator because the Earth's axis is tilted that angle to its orbit. The sun appears to move along the ecliptic because the Earth's orbit around the sun places it in front of 12 different constellations. These constellations are called the Zodiac. However, they are not the same as the signs of the Zodiac. The areas of the signs can be displayed above the map. You can see that the constellations for which they are named have all shifted about 2 hours or 30 degrees to the left over the last 2,000 years. This is called the Precession of the Equinoxes, and it's due to the wobbling of the direction of the Earth's axis every 25,920 years. The sun currently appears to be in the constellation Pisces during the spring equinox. 2,000 years ago, it was in Aries, and will eventually be in Aquarius. You may have heard of the Age of Aquarius. There is even a song about it you can listen to on YouTube. The plane of the moon's orbit around the Earth is nearly parallel to the ecliptic, but the slight difference is why lunar and solar eclipses are rare events. When a full moon occurs, it will always be 12 hours or 180 degrees from the sun on the sky map. Full moons always rise as the sun is setting. Quarter moons are 6 hours from the sun. A waxing quarter moon begins to rise at noon. A waning quarter moon will set at noon. Most of the planets orbit the sun in the same plane as the Earth's orbit. The sun spins around an axis that is perpendicular to most of the orbits. The closer a planet is to the sun, the shorter its orbit. Mercury completes its revolution around the sun in only 88 Earth days. The circumference of its orbit is shorter than other planets, but it's also traveling faster along its orbit. The sizes of the sun and the planets are not to scale with the size of the orbits in this image, but you can see that the orbit of Mars is larger than Earth's. It takes Mars almost 2 years to orbit the Sun. When the Earth overtakes it, it causes the Mars retrograde, the apparent reverse in direction of its movement along the ecliptic. If we zoom out, we can see the orbits of Jupiter and Saturn. The blue planet in the distance is Uranus, which cannot be seen without a telescope. Jupiter takes almost 12 years to orbit the Sun, and Saturn takes 29 and a half years. Jupiter actually has 95 moons which orbit it. On a clear night, you can see its 4 largest moons with a pair of binoculars. If the following night is also clear, you can see that the position of the moons have changed. Galileo was the first person to see these moons orbiting Jupiter in the year 1610 using a homemade telescope. This was an important discovery that changed the way people viewed the world above us. The Greeks had accepted that the Earth was a sphere since the time of Aristotle. Around 50 years later, Aristarchus proposed that the Sun was the center of the universe and the Earth revolved around it. 400 years later, Ptolemy compiled the observations of Greek geographers and astronomers into an atlas. Remember that Mercator would later use this atlas as the basis of his world map. Like most people at the time, Ptolemy believed that the Earth was the center of the universe, and everything revolved around it. His atlas included detailed tables that accounted for the retrogrades of planets with loops within their orbits. In 1543, shortly before his death, Copernicus published a book which described a sun-centered model of the universe. Galileo's discovery seemed to confirm this model. A few years later, the astronomer Kepler published a much more detailed description of a sun-centered model. It contained the laws of planetary motion that we still use today. They provided the math and geometry for the size, shape, and velocity of the orbits of each of the visible planets. A little more than a century ago, astronomers proved that the Sun was, like all the other visible stars, revolving around the center of a galaxy. The first galaxies outside the Milky Way were also then discovered. Considering that stars are revolving at both great and different speeds around the galaxy, you'd expect that the positions of the stars on the sky map would be changing. And actually they are, but very slowly. It takes more than 70 years for zodiac stars to move just 1 degree on the map. The distances of stars in the same constellations change in different ways and in their order of brightness. However, because the galaxy is so large and all its stars are moving around its center, the sky map changes slowly. The study options are different for the sky map than the 17 Earth maps. The hours of right ascension is selected by default in the sky map study mode. You can alternatively display the months of the year or the signs of the zodiac above the map. The Stars button displays icons for the 100 brightest stars. Pointing the mouse over these icons will display information about a star next to the map. The Constellations button displays the names next to each constellation on the map. Buttons with the numbers 1, 2, 3, and 4 appear on the next row, and the Brightness button to the left is selected by default. Initially, the number buttons will each display 25 star icons by the magnitude of their brightness. Clicking the Distance button will cause the number buttons to display icons according to their distance from us. This is the sky map with the icons displayed for all of the 100 brightest stars. The size of the icons are based on a star's magnitude of brightness. In the early 20th century, astronomers discovered they could categorize stars by their magnitude of brightness, not their apparent brightness, which is also determined by their distance from us, but their absolute magnitude of brightness. This is measured with an inverse logarithmic scale, but it can also be expressed with a simpler luminosity scale, in which our sun has a luminosity equal to 1. The brightest stars can have luminosities of 1 million, and the dimmest stars are less than 1,000th as luminous. When stars are also categorized by their temperatures, which correspond to the color of their light, a pattern emerges. Most stars are classified as main sequence, with each dot representing a star. You can see this forms a diagonal curve of very hot and luminous stars, starting in the top left and ends with cooler, less luminous stars at the bottom right. Above and to the right of the main sequence, you can see clusters of dots that are labeled as giants and supergiants. In the bottom left are the white dwarfs. Stars evolve over time. They begin when hydrogen molecules are attracted by gravity to form a sphere. The gravitational force then causes the hydrogen to form helium atoms deep in the core of the star. This fusion process is what generates light and energy. The amount of hydrogen a star begins with determines how it will evolve. Our sun is considered an average-sized star. It has been fusing hydrogen for about 5 billion years. Some of the helium has also fused into carbon and oxygen at the core. The sun is expected to continue this process for another 4 billion years. But as the denser core grows, the hydrogen fusion process shifts to a spherical shell outside the core, and that will cause the sun to expand into a red giant. Its core will eventually collapse into a white dwarf and will separate from the outer shell, which becomes a nebula of gas and dust that can potentially form a planet. The evolution of a massive star that contains more hydrogen happens more quickly. These very luminous, very hot stars not only fuse hydrogen into helium and lighter elements like carbon at a much faster rate, they also fuse heavier elements within their cores like iron, gold, and uranium. They expand into red supergiants as their hydrogen dwindles, and then explode into supernovas, which can either result in neutron stars or black holes. This diagram shows the additional classifications of giants and supergiants of stars as they transition from the main sequence. Note that average stars like our sun are considered dwarfs. The sun is categorized as a yellow dwarf. There are many red dwarfs in our galaxy, but they don't emit enough light to be visible to the naked eye. Below the red dwarfs, there are brown dwarfs, which don't fuse enough helium to emit any light. The planet Jupiter is a brown dwarf. Jupiter is one of the brightest objects in our sky, but what we see is reflected sunlight. This is how the 100 brightest stars are positioned on the Hertzsprung-Russell diagram. For example, this is the plot for Sirius, the brightest star in our sky. It is actually a binary star, a white dwarf revolving around a main sequence star. This is an example of the information that is displayed next to the sky map when you point at a star's icon. Clicking on a star icon will open a new tab with a star's Wikipedia article. The order of brightness of a star is given first, followed by its radius compared with the Sun. Sirius's main sequence star has 1.7 times the Sun's radius. Alpha Canis Majoris is the scientific name for Sirius, which is 9 light years away from us. Deneb is the 20th brightest star in the sky. It's classified as a white supergiant with a radius that is 203 times that of our Sun. Alpha Cygni is 3,000 light years away, which is the furthest distance of any of the 100 brightest stars. Our galaxy is about 100,000 light years wide, so the stars we can see without a telescope are in the same area as we are in the galaxy. There are roughly 100 billion stars in our Milky Way galaxy. The names of stars and constellations are not easy to remember because they are primarily Greek, Latin, and Arabic. For example, Deneb is Arabic for tail. The constellation Cygnus is Latin for swan. Shortly before telescopes were invented in the 1600s, Johann Bayer created a system of naming stars that eliminated the Arabic names. He used the sequence of Greek letters like alpha, beta, gamma to designate stars in a constellation by their brightness. Deneb became Alpha Cygni. Cygnus is a Latin noun and Cygni is the Latin adjective. Without a telescope, Bayer couldn't always identify the correct order of brightness. He relied on Ptolemy's magnitude classifications and simply listed the northernmost star first if more than one star in a constellation had the same magnitude. Ptolemy did not include stars in the southern hemisphere because Europeans had never seen them before they sailed south of the equator. Bayer devised his system mainly to give names to stars like Alpha Centauri, which doesn't have any other name. Some southern constellations were given English names in honor of the newest inventions of their day, like clock and telescope. On the sky map, many of the Latin names of constellations have been translated into English. The sky map quizzes will help you to learn the names of stars. They group stars by their magnitudes of brightness in 4 separate quizzes. Sketching and labeling stars and constellations is also an effective activity for learning their names. However, there are some differences from how the Earth maps are sketched. The buttons provide you with the same tools, but there are no west and east buttons for copying left and right sides of the map. Instead, there are 4 number buttons. These let you check whether you have correctly copied stars according to their magnitude of brightness. You can see that the default dot size is 4, which is best for bright stars, but should be decreased for dimmer stars. Constellations, unlike coastlines, are not actually real. Other civilizations like the Chinese and the Mayans grouped stars in completely different constellations. When you sketch the sky map, you start by using the dot tool to locate stars. Use blue or red dots to make associations for remembering their locations inside the 24 primary squares. Magnitude 1 stars should be located first. Clicking the number 1 button will dim the constellations and display these stars' icons, which your dots should overlap. Note any stars you missed, and then click the dot button to continue. Use the size field to reduce the size of dimmer stars to approximate the same sizes of the icons. Size 4 works for magnitude 1, size 3 for magnitude 2, and size 2 for both magnitudes 3 and 4. Size 1 is too small for individual stars, but it's the best choice for Orion's belt. These three stars are actually magnitudes 2 and 3. Size 1 dots result in the most accurate spacing between these stars. The belt makes Orion one of the most recognizable constellations in the sky. Stargazers often check out the magnitude 1 star above it. Its name is Betelgeuse, and it's the next red supergiant that is expected to explode into a supernova. Sketching constellations is best done by tracing them with the line tool set to black and a size of 1. The style of constellations used on the sky map were developed by H.A.Rey in 1952. Several of them have replaced the former designs. Compare the traditional style of Gemini with the more descriptive design by Rey. Rey is better known for his series of children's books based on a monkey named Curious George. However, his book, The Stars, is recognized as an excellent introduction to astronomy. Click the grid button to view your sketch of the sky map. You needn't draw all the constellations, especially ones without any bright stars. You can just label those. Using black for constellations and blue and red labels for stars is the clearest way to label them. The best activity for complementing your study of the stars is making a star globe. The materials and steps for making a star globe are similar to an Earth globe. After you make the crayon grid, you add the ecliptic with 2 contrasting colors. I used yellow and red. My yellow segments of the ecliptic correspond to even-numbered months. You then add the Milky Way before sketching the constellations. Remember that constellations are formed by connecting stars with straight lines. But on your ball, you first locate the stars with the same marker that you use for the lines. Then you use a white marker to indicate the brightness of stars. You can erase the grid before or after completing the stars. If you compare a star globe with an online star chart, you will see that your basketball has become a guide to the night sky. The stars that will be visible after sunset are to the left of the position of the sun on the ecliptic. The stars that will be visible before sunrise are to the right of the position of the sun. This is a view from the northern latitudes after sunset in mid-May or an early morning in November. The yellow and red ecliptic segments below Leo show the position of the sun in August and September. There are links to a couple of online star charts in the gallery section. They attempt to identify your latitude and time zone based on your IP address. Tilt the top of the ball toward or away from you to adjust the view to your latitude. You can see the Big Dipper constellation in the top left of the online star chart and on the top left of the ball. When you compare the relative positions of the stars of Leo and Gemini, it's apparent that the star chart shows more of the sky than the ball does. In this view of the ball, we see the Great Square and the 3 bright stars of the Summer Triangle to its right. Deneb is the bright star to the right of the ball's curved stripe. When we compare these stars with the chart, we see that less sky is again visible on the ball. This can be explained by comparing a planar projection with an overhead view of a globe. You can't see areas immediately above the equator on a globe because they are turned almost 90 degrees away from your line of sight. However, star charts are based on looking at the sky while facing different directions. This planar projection of the Earth is based on a center contact point at 90 degrees north. The contact points of star chart projections are based on your latitude and longitude. The chart and star globe are both models of the celestial sphere. However, we are inside that sphere at the center, so it's possible to see a full 180-degree view of it. Stargazers also know that when you attempt to view stars on the horizon, the amount of atmosphere we look through usually blocks the light. The celestial sphere is just a geometric concept for calculating the declination and right ascension of stars and planets. The sky map doesn't have a scale. The distances between stars on the map are unrelated to the actual distances between them in our Milky Way galaxy. The term double star refers to two stars that are nearly aligned from our point of view, but can actually be hundreds of light years apart. We are closer to some of the stars in the Swan constellation than Deneb is. The sky globe is an example of a convex-concave illusion. This hollow face illusion is another example. These two faces are views of the front and back of the same plastic mask. The sky globe is a useful illusion. If we could view the stars from outside the celestial sphere, they would be flipped vertically to how they appear from the Earth. For example, the Great Square would actually be to the right of the summer triangle. However, that star globe would not be as useful for identifying stars and constellations in the sky. There are other types of objects in the galaxy besides stars, including planets. Planets outside our solar system are called exoplanets. Identifying planets that are similar to ours is a primary goal for many astronomers. They now have space telescopes above the Earth's atmosphere, which are capable of identifying them. The good news is that there are billions of planets in our galaxy. However, a planet that offers the kind of environment we need has not been found yet. The more you learn about the universe, the more precious the Earth appears to be. The benefits of Earth and sky camp activities are obvious for the study of geography and astronomy. They can also prepare students to better understand advanced subjects like geology, ecology, and economics. Astronomy will complement core subjects like physics and chemistry, just as geography complements the study of history. The manual map puts the world in your hands. When you can accurately communicate with others about the world, you can work together to make it a better place. Check out manualmemory.net to get started with Earth and Sky Camp, as well as other visual learning applications.